Hi, my name is Caleb Froelich, and I'm going to be presenting on my ground source heat pump coil optimization project. If you're not super familiar with what a ground source heat pump is, here's an airflow diagram of the system that my dad, a Walla Walla University engineering graduate, and I are installing in our home. For our analysis, we are interested in how much heat can be transferred between the water and the air flowing through the GSHP coil. The more heat transfer, the more BTU hours of cooling provided. The amount of cooling is related to two variables, the rate of water flowing through the coil in units of GPM, and the amount of airflow through the coil in units of CFM, cubic feet per minute. The goal of our analysis is to minimize the cost per BTU of cooling provided by the ground source heat pump coil. To do this, I had to find the cost function of the well pump and fan motor. The development of the fan motor cost model was easy enough. I simply measured the current and voltage for a variety of different CFMs and created a plot as shown. The well pump cost model was slightly more challenging due to the induction motor that our well pump uses. The starting current of an induction motor is as high as 5 to 7 times the normal full load current. Thus I created two models, a simplistic model without the startup current and a model with it. I assumed a startup power of about 500 watts. We also had to find the thermal efficiency of the coil. In other words, how many BTU hours were produced as a function of our two variables, GPM and CFM. This proved to be fairly difficult to measure. Thus I partnered with Baltimore Air Coil Company, who helped me design a coil similar to our coil that could be tested with their software. The results of this analysis produced, well, a lot of data. And for each one of these measurement sheets at a fixed GPM and CFM, I was able to compute the BTU hour output. Doing this many times, I fit the data points to a curve on MATLAB and obtained a function for the heat transfer of the coil in terms of CFM and GPM. Thus, formalizing our optimization problem, we seek to minimize J of x, which is the cost of the fan and the cost of the pump, both in watts, divided by the coil output in BTUs per hour. The constraint on Q coil represents 1/2 of the typical cooling demands of an American household, and we have some feasible bounds on our two variables. Just as a reminder, here are our mathematical models, and here is a graph of our objective function without the constraint on Q coil. The three main criteria I looked for when selecting an optimization algorithm were a repeated convergence to the optimal value, an ease of use of the program, and low computational demand. For these three reasons, I chose the GRG method. It has several advantages. Since it is gradient-based, it converges quickly to the minimum, and its implementation in Excel made it easy to integrate my data with the optimization process. The few disadvantages of the GRG method is that it is highly dependent on initial conditions, and it needs smooth, continuous functions. From looking at our objective function, I concluded that neither of these were concerns. Of course, I used the Excel solver add-in with the GRG nonlinear method selected. By solving our optimization problem, we get a constrained minimum of 0.1197 watts per BTU hour. Technically, that's a lie. Since CFM is discrete value, I had to re-optimize at the closest two fan settings. Thus, our true minimum is 0.1198 watts per BTU hour at 1,518.95 cm and 2.308 GPM. Now, the obvious question is, how do these results compare to other HVA solutions? Through our analysis, we found our optimization results to be fairly comparable with the average Energy Star HVAC unit. But how does it compare to a cheaper solution? Well, I chose to compare my results to the ductless Fujitsu 9RLS3 mini-split, since we have several of these systems installed in our home. And to be honest, the Fujitsus kind of blew our results out of the water. Now, it goes without saying that our assumptions did have a significant impact on the economics of our solution. Through our analysis, we made two key assumptions. One, we assumed, in part, the efficiency of the coil. And number two, we assumed the pump starting power requirements. Now, our system is pressurized at 40 psi, and thus the startup cost of the pump would almost be negligible for our house. So if we used the simple model and re-optimized, we would get a solution that is 40% cheaper than the Fujitsu. Additionally, using a more efficient pump would also help matters. Most ground source heat pump Systems use smaller low-flow pumps, which are way more efficient than a well pump. Solving this problem in reverse, we find that we would need a well pump with a startup power equal to or less than 78.42 watts for the system to be as efficient as the Fujitsu. So that's my analysis. If you have any questions on this project or how an Arduino can be used to solve all your cooling needs, please feel free to reach out to me via email at caleb.froelich@wallawalla.edu or message me on Teams. Thanks.